Good evening. Our today's topic is law of conservation of momentum. Of system. So in order to understand this whole law, we should know about the certain terms. Like first term, what do you mean by momentum? If I'm saying that I'm considering the momentum of a body, then what is that term momentum is? Momentum is the product of mass and velocity of object. Like for example, if this body have a certain mass of 2 kgs and is proceeding in the forward direction with the velocity of, let's suppose, 3 meters per second, then what will be the momentum? We usually represent the momentum of a system by small p, and it will be the product of mass and velocity. That is 2 into 3. That is 6 kgs meter per second. So in this way, we evaluate the momentum of the system. And now, this word system we are using again and again. I just want to clear that term. What is a system? Like anything in our environment which we are considering for the study. Like here is a marker. I just want to study its position. I just want to study its momentum, its velocity. So anything which I am using for considering its motion, its position, its velocity, anything which is used for study is we generally call the system in the language of science. All right. So now let's come to our main topic, that is law of conservation of momentum of system. Right. So what does this law states that according to this law, the momentum of the system remains conserved with the condition that the system should be an isolated one. Now, what do you mean by isolated one? Isolated means that is the net force acting on the system should be 0. So this is our law of conservation of momentum says that whenever there is a system that we are going to study, right, it has some certain momentum, like it has some certain mass, it is moving with a certain velocity, right? It has some certain momentum, and that momentum of the system will always remain conserved, but with the condition that the force acting on the system should be what? 0, right? So we have just studied this law of conservation of momentum theoretically. I just want to clear this definition mathematically as. Now, let's suppose that we are considering this system, and this system is comprised of the two objects, object A and object B, right? Let's suppose object A has mass ma and object B has mass mb, right? And object A is moving with the velocity ua and object B is moving with the velocity ub. All right. So what this law of conservation of momentum says, let's suppose before collision of these two objects, the velocity of A is ua, right? And the velocity of B is ub, right? And also suppose that before, now mass is a constant quantity, so it doesn't change before and after collision, it will always remain conserved. It will always remain constant. Okay. So after that, after collision, when there is a collision takes place, so when there is a collision takes place of these two objects A and B, obviously its velocity will change. So the velocity of A now becomes, let's suppose after collision, it now becomes VA and velocity of B now becomes VB, right? So total momentum of the system. Now this system is comprised of two objects A and B. It is equals to momentum of A plus momentum of B. Now let's suppose we are considering this term before collision. Before collision. So can you tell me, before collision concept, A is moving with the velocity ua and B is moving with the velocity ub. Now before collision, if we consider total momentum of the whole system, now we cannot individually consider only A, we cannot individually consider only B, because this system is comprised of the two particles A and B. So we should consider it as a integrated quantity. So before collision, if I am considering the momentum of the system, I have to add up the momentum of A and B. And it will be equals to what? MA UA plus MB UB. So this is before collision, right? Now, if I'm considering the momentum of this system after collision, so what it will be? So I am just changing these terms, after collision terms. Now, you know that mass will remain always constant, so I'm not changing it. So here I have VA, here I have VB, and here I have just changed after collision. Now, after collision, the momentum of the system now becomes what? Of A, that is MA, VA. Now, velocity becomes changed, so I am just using here VA. Now, V, MB, VB. So this is the momentum of the system after collision. And one thing you just have to notice that there is no net force acting, external force. There is no net external force acting on the system. And in that very case, so what this law states that the momentum of the system always remains conserved. That means even before the collision and the result after the collision, the momentum result will always remains conserved, always remains constant. So how can I write here? So according to this system, this law, momentum of system before collision should equals to momentum of system after collision. So just using these terms, what I get, that means this law states that MA, UA, this is the momentum of A, MB, UB, this is the momentum of B, and this whole term is when we are considering before collision event, and after collision it becomes MAVA plus MBV. So this is what momentum of A before collision, right? And this is momentum of B before collision, and this is momentum of A after collision, and this is momentum of, here I should use VB, momentum of B after collision. So this is the momentum of the system, right? Before collision, this is the momentum of the system after collision. So why I have just put it these two equal, because these always remains constant. So it should be a constant quantity which doesn't change with respect to time. It doesn't change with respect to time. So these two quantities, the summing of these two quantities always remains conserved. Like if the sum becomes sum of these two becomes 2, then these two should also comes up with the 2 quantity, right? Only 2 numerical types. So this is our law of conservation of momentum says. So now let's get started with its derivation also. So we should consider that what is the derivation of this theorem, because our physics is only linked with the derivation, right? We cannot accept the fact theoretically. We just need its proof also. So let's suppose that here I have this object A and here I have this object B, and we are considering these two body systems, right? And object A is moving just with the velocity UA, and object B is moving with the velocity UB, and object A has mass MA, object B has mass MB, right? And so when before collision, they are moving, towards each other, right? And at the time of collision, so this is a case of before collision, right? And at the time of collision, like A and B, when these two objects collide with respect to each other, so object A is imposing some force on object B. Let's name that as FB, and object B is imposing some force on object A, and let's name that FA, right? So this is the case during collision, right? During collision, like there is some certain time when the collision took place. So here we should consider that F is what? The force by B on force A, on the object A, right? And FB is what? The force on object B by object A, right? And after collision, what happened? Here is A, here is B, and there is a collision, right? So now object A is moving with a certain different velocity and object B is moving with a certain different velocity, right? So I'm just rubbing it out. I'm just writing it that now F is what? Force on A by B, right? And FB is what? Force on B by A. And by Newton's third law, you know that these two forces should be equal in magnitude and opposite in direction. So can I write that FA is minus of FB, right? Can I write it as this? I'm marking it as equation number 1 because I'm going to use it later on, right? So FA equals to minus of FB, right? Now, when the collision took place, here I have this object A and here I have this object B, right? When the collision took place, At the time, according to Newton's second law, according to Newton's second law, what happened is, you know that F is equals to minus dp by dt. That is minus change in momentum, right? Divided by time taken, right? Divided by time taken of that momentum change, right? Now, if I am considering the force on object A, right? If I'm considering FA, that is the force on object A, so I should consider the change in momentum of object A. Yes. So if I'm using here FA, that is force on object A, so I should consider that change in momentum in object A. So I'm just writing here change in momentum in A divided by total time taken. Let's name it by small t. Let's suppose that small t time will be taken during that momentum change, right? And after that, what is the change in the momentum in A, right? We have to evaluate that numerator term. So change in momentum in A should be equals to what? Should be equals to final momentum of A minus initial momentum of A. So can you tell me what is the final momentum of A? Obviously, the momentum that becomes after the collision, and it will becomes equals to ma va. And what is the initial momentum of A? Obviously, ma and initial velocity of A, right? So this is a total change in momentum of A, right? So can I write now according to second law? According to second law of motion, what I get? Fa should be minus change in momentum. And now change in momentum in A is what? Ma Va minus Ma Ua divided by total time taken for that change in momentum. And I am using here, I'm marking it as equation number 2 because I have marked equation number 1 as F equals to minus of Fb. I'm going to use that also in the later one. So after that, in the similar manner, can we also write Fb? So what is Fb over here? Fb is equals to Mb Vb minus Mb Ub divided by T. Here is the force on the object. Here is force on B, and this term is what? Change in momentum in B. And T is what? Time of application of that force, right? And T is what? Time of application of force, right? So now I'm marking it as equation number 3. Now this Fa should equal to Fb, but with a negative sign. So I'm going to use equation number 1. So I think you have noted this till now. So I'm going to rub this. So now using equation number 1, that is Fa is equals to minus of Fb, and Fa is here what? Ma Va minus Ma Ua, that is changing momentum of object A divided by time, and it should be minus of Mb Vb minus Mb Ub divided by time. And just manipulate this, and what I get? Mb Ub minus Mb Vb divided by time, and just cancel time. right? And what will we get is, I'm just rubbing it out. What will we get? We just need to manipulate these terms. Like in the left hand side, just replace all use terms, like use velocities terms. So what I get is MBUB plus MAUA is equals to, I've just manipulated these terms, and this term is taken over here. So it should becomes plus over here. So, and this term should be taken over here. So it should becomes plus. So what I get, MAVA plus MBV, right? And this is what? This is total momentum of system. Obviously, these are used terms, so before collision, as I have considered the velocity before collision as UA and UB, and this is momentum of system after collision, right? And this is going to be equal even after collision, and it is always a constant quantity. That means this quantity does not change with respect to time. And this is what our law of conservation of momentum says. So I hope that you understood this concept of law of conservation of momentum. Okay, goodbye, take care.